Robert Bryce is coming up here in just a minute and is going to be very familiar to you. You've probably seen him on BBC or the CNN network, CNBC, Fox, PBS, MSNBC. He's senior fellow at the Manhattan Institute. He's written several visionary and really impassioned books that are about energy, and all have had rave reviews by the Wall Street Journal and the New York Times. His latest book is entitled Power Hungry: The Myths of Green Energy and the Real Fuels of the Future, from Austin, Texas. Please welcome Robert Bryce.
Good morning. I have 5 points that I'm going to make in the next 40 minutes. First, scale. 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 I'm going to spend a lot of time discussing the first point because it is the one that is seldom discussed by policymakers and by the media. Second, quick lesson on Physics 101. Third, density. Fourth, top of the second inning, a brief rundown of where we are in the shale revolution. And finally, end-to-end, natural gas to nuclear. Discuss why those are the fuels of the future. I'm not going to argue that coal and oil are going away. They clearly are not. So, first, scale. Who can name the country which between 2001 and 2010 had the biggest percentage increase in CO2 emissions? Anyone? China's a good guess. Anyone else? Vietnam. Who can name the country which over that same time period had the biggest percentage increase in electricity generation? Vietnam. Who can name the country which over that same time period had the biggest percentage increase in coal consumption? Vietnam. Outstanding. You've had your coffee. Why do I bring that up? Yes, it's an interesting fact to know and tell, but further, I think it goes directly to the point of one of the questions that we just heard. What about CO2? What about climate change? What about international policy on CO2? And my answer to those questions is Vietnam. Look at a country which has a per capita income of $1,200, average per capita income of $1,200 per year, 90 million people desperately trying to come out of the dark and into the light. In Hanoi, in Ho Chi Minh City, Saigon, Hue, they are not talking about climate change. They are not discussing Al Gore's latest book. They are building coal-fired power plants as quickly as they possibly can. I'm not here to argue the science of CO2 or global warming one way or another. I'm a resolute agnostic. Tell me CO2 is good, tell me CO2 is bad. I don't care. I read both sides of the arguments. I'm tired of the nastiness of the discussion. Which tribe are you in? Are you a catastrophist, or are you an alarmist? You know, or are you a denier? Well, surely if you work for ExxonMobil, you must be a denier. That is the way that the argument has devolved into this nasty tribal discussion. Which tribe are you in? And instead of asking, what then? If you think CO2 is bad, then what? What is your solution? Who will you send to Beijing, to Saigon, to Mumbai to say, no, you shouldn't build any more coal-fired power plants? The issue is the tyranny of big numbers. The issue is one fundamentally of scale, and I thought Rob Gardner's presentation really walked us through a lot of those scale numbers, but let me give you a different spin on that. And use a different metric. All due respect to ExxonMobil, they do a fantastic job. BP does a great job, IEA, EIA. But look, they use million tons of oil equivalent. They use trillion cubic feet of gas, billion cubic feet per day, terawatt hours, megawatt hours, million tons of oil equivalent, quadrillion BTUs, which I think is the absolute worst of all of them. The metric I like, and the one that I try to normalize to, so you have a common denominator, is million barrels of oil equivalent per day. The public and politicians, ask them what a terawatt hour is, ask them what a kilowatt is, a kilowatt hour. No idea. None. But I think as a general rule, the public understands what a barrel of oil is. They know approximately what it costs because they buy gasoline, they buy fuel, and they're familiar with the price, and they hear about it more than any other. So, the scale, the tyranny of big numbers. What is our global consumption today? It's roughly 247 million barrels of oil equivalent per day. 247 million barrels of oil equivalent per day. That's 30 Saudi Arabias. Since the 70s, the Saudis have been producing roughly 8.2 million barrels of oil per day. General public doesn't know how much the Saudis produce, but they know it's a big number. 247 million barrels of oil equivalent, 30 Saudi Arabias, and of that we get 87%, roughly 215 million barrels of oil equivalent per day, or 26 Saudi Arabias from coal, oil, and natural gas. We get 10 Saudi Arabias in oil, 7 from natural gas, and 9 from coal. So we can like Al Gore, hate Al Gore, we can say he's right, we can say he's wrong, we say he's somewhere in the middle. The question is, if you believe CO2 is bad, then where will we find that 26 Saudi Arabias per day of carbon-free energy? That's the challenge. If you believe CO2 is bad, then where will you find this vast quantity of energy to displace carbon-based fuels? That's the challenge. And it's one reason why I'm convinced that what has happened over the last decade, the decade of multiple IPCC reports, the decade of Al Gore, he won the Academy Award, the Nobel Prize, the Emmy. We had meetings in Bonn, Copenhagen, Durban, all of which aimed at some kind of carbon regime, restrictions, taxation, etc., cap and trade. What happened? Nothing happened. Why did nothing happen? Because of countries like Vietnam, of countries like Brazil, India, China, you know the rest. This was the environmental issue of the last decade, and yet what happened? Global CO2 emissions increased by 30%. Just for reference, between 2001 and 2010, the 5 countries with the biggest percentage increase in CO2 emissions: Vietnam, 137%, China, 123%, Qatar, 115%, Trinidad, 84%, India, 78%. Nominal increases, of course, the more important number, China, an increase of 4.6 billion tons. Think about that. In the last decade alone, China's CO2 increase nearly matched the entire CO2 output of the United States. India, 748 million tons, Saudi Arabia, 220, Iran, 212, and South Korea, 174. Those 5 countries combined accounted for about 80% of the CO2 increase globally over that time period. And over the past decade, U.S. CO2 emissions fell, by 4.4%. Put another way, U.S. CO2 emissions over the last decade could have gone to zero. Could have gone to zero, and yet global carbon emissions still would have increased. And to me, the question that then poses is, and by the way, you will never hear that number, you will never hear that fact, and it is a fact, from the Sierra Club, Greenpeace, Natural Resources Defense Council, or any of these other lobby groups arguing for CO2 caps, taxation, etc. But given that fact, why would the United States ever put in place a cap and trade system? Why would they ever have an emissions trading scheme like the one in Europe, which has now clearly been a failure? Makes no sense to me. The U.S. is reducing its CO2 emissions more quickly than any other country in the world because of market forces. The shale revolution has resulted in the U.S. reducing its CO2 emissions more quickly than any other country on the planet. Not my calculations, those are from the IEA. Scale, scale, scale. Over the past decade, global coal consumption has increased by about the same amount as all oil, natural gas, nuclear, and hydro increase combined. Scale. Last year, in 2011, global coal consumption increased by about 3.9 million barrels of oil equivalent per day, roughly 1/2 of a Saudi Arabia. Last year, that increase in coal alone was roughly equal to all of the contribution of all global solar, all global wind, and all biomass combined. Let me say it again. Last year, global coal consumption increased by as much as all the contribution from all solar, all wind, and all biomass. Scale. Talk about scale and electricity. Over the last 30 years, roughly, since 1985, global electricity demand has been growing by about 450 terawatt hours per year. It's roughly one Brazil. Brazil's electric consumption is a little bit more than 450 terawatt hours, but nevertheless, from 1985 to today, global electric demand has been increasing by Brazil a year, and you look at projections, and it is expected to increase by about a Brazil a year from now through 2035. Okay, well, if we want to do that, then, and we wanted to meet that demand with wind energy, what would that require? It would require installing a whole lot of wind capacity. Obviously, it would require covering a land area of roughly 35,000 square miles of territory, of land, using 2 watts per square meter. It's a power density number. I'll come back to that later. A land area roughly the size of the state of Indiana every year just to meet demand. I'm not as bullish as ExxonMobil on the future of wind. There's a backlash globally against the wind business that is global, and it is growing. Let me give you another metric to compare that to. So 35,000 square miles per year. What it means is we would have to cover a land area of roughly 4 Manhattan Islands, approximately 100 square miles of land territory per day would have to be covered with wind turbines just to meet incremental global electric demand. What about solar? I'm a believer in solar. I like where the solar business is going. By the way, I'm opposed to all energy subsidies unless I'm getting them. It's true. I live in Austin, 200 miles south of here. City of Austin paid 2/3 of the cost for my 3,200-watt solar panels system on the roof of my house. Provides about 1/3 of the electricity my family and I use. So I want to eliminate all energy subsidies, but I'm happy with the one I got. Thank you, City of Austin. My neighbors come by, look at my turbines, or my solar panels, and say, boy, I love your wind turbines, your solar panels. I love your solar panels. And I say, well, thank you. You helped pay for them. 450 terawatt hours per year is our growth in demand in electricity. What would it require if we were to meet that demand with solar? Well, we all know that Germany is leading the world in solar capacity. They have about 25,000 megawatts of installed PV capacity. Last year, that 25,000 megawatts of installed capacity provided 19 terawatt hours of electricity. Math is easy from here. If we were going to use solar PV and assume Germany's numbers are about the right ones, we would have to install roughly 23 times Germany's installed PV base and do so every year merely to keep pace with demand. Let's assume we put them in a sunny place instead of Germany. Well, we still need 10 times Germany's installed base, and we have to install it every year just to meet incremental demand, not to displace any coal, not to displace any natural gas, nuclear, or any of the other conventional sources. This is a daunting number. It is a daunting reality, and they're not my numbers. They're easily fact-checked. Go to the BP Statistical Review. Scale and coal. Let's look at Germany. In the wake of Fukushima, the Merkel administration said, we're going to phase out nuclear. Okay, fine. What happened just a few weeks ago? RWE opened a new lignite-fired power plant near Cologne. That one plant by itself will produce roughly 16 terawatt hours of electricity per year. One plant. A 2,200 megawatt lignite plant will produce by itself nearly as much electricity as all of the solar PV in Germany. Scale, scale, scale. We hear over and over about investment in green technology. I'm all for it. There's some fascinating developments that are happening. A few weeks ago, I was in Pittsburgh looking at a company called Aquion Energy. If you're interested in it, Aquion. I think these guys have broken the code on grid-scale battery storage. A lot of money is flowing into green tech, clean tech, et cetera. The UN estimates in 2010 total investment in that sector was around $211 billion. It's a lot of money. This year, according to IHS, however, the global upstream investment will be $1.2 trillion. And of that, at least $400 billion will happen here in the United States. Scale, scale, scale. Physics 101, very quickly. We don't give a damn about energy. We don't give a damn about energy. What we want is power. And we demand that we have power availability 24/7, 365. The lights in this room could be coming from a coal-fired power plant, could be coming from a nuclear reactor, wind turbine, solar panel, fuel cell. Maybe the Ritz-Carlton has some Cummins generators down in the basement. I don't really care where the electricity is coming from. I don't really care about what fuel is driving these lights. What I care about, and what Rob mentioned just a few minutes ago, is that when we go to the wall switch, the power comes on. We're not as interested in the form of energy that we consume as we are in our ability to make energy flow. And therein is the difference. How many engineers in the audience? A few. Physics 101, basic engineering. Energy is the ability to do work. Power is the rate at which work gets done. Energy is the ability to do work. Power is the rate at which work gets done. Rates are more telling than sums. Energy is a quantity, an amount, a barrel of oil, 1,000 cubic feet of gas, a ton of coal. Power, by definition, is a rate. 1 joule per second equals 1 watt, and it's the per that matters. The per is the rate calculation. 1 joule per second equals 1 watt. Energy and power are not the same, yet they are continually confused in the energy sector and even in the electric sector itself. And it's one of the reasons why, in my view, the renewable sector has been able to get a free ride on other electric providers throughout the grid. And it even goes to the basic terminology, the most basic terminology in the industry, the power purchase agreement. When wind projects are launched, solar projects are launched, they generally have to have a power purchase agreement in place. They have to have a utility saying, we will buy X from you over X time. But what they are signing is, in fact, not a power purchase agreement. It is an energy purchase agreement. The most fundamental document in the industry is, in fact, misnamed. Energy is measured in megawatt hours. Power is measured in megawatts or watts. Choose whichever number or whichever metric you like. Why does this matter? We're here in Texas. A year ago, last August, it was ridiculously hot. Long drought. And we had numerous days that month of 100-degree temperatures. Power demand, measured in megawatts, was at record highs, 69,000 megawatts of peak demand on weekday afternoons between 4 and 5 o'clock. Texas has more wind energy capacity than any other state, over 10,000 megawatts of capacity. And yet, during those times of peak demand, when power prices were highest, when power demand was greatest, how much power was coming from all of the installed wind generation in the state? Less than 1,000 megawatts. So when power demand was highest, here you have a source of energy that could not deliver power, and they were not penalized for it because their contracts call for them to deliver energy in the form of kilowatt hours or megawatt hours, not power. Rob Gardner referred to this earlier on about figuring in the cost of backup for renewable energy. What is the cost to the grid of making sure that we have lights all the time? Imagine if you're in the oil and gas business and you sell a product that only works a third of the time. Here, let me fill your car and you can drive it. I'm not going to tell you what third of the day, how many 8 hours of the day you can drive it, but rest assured it's really good gasoline. How long would you be in business? Not long, I'd wager. Why do I bring this up? Because it's critical to our discussions of these issues. Our politicians are largely not engineers. In fact, we have, I think in the House of Representatives now, one engineer. We have over a dozen doctors. The rest of them are lawyers. Why did they go to law school? Because they couldn't hack the math for engineering. This is the reality. But what is the problem is that they are innumerate. They're not only innumerate, they're scientifically illiterate. They don't understand the differences between energy and power, and they don't have the time to do the simple math like I've just given you. And so therefore, they assume wrongly energy is equivalent to power, and they assume wrongly that we can scale up solar and wind to meet overall demand, and we know what that results in: bad policy. So yes, why did I write my last book, Power Hungry? Rob mentioned it because I wanted to address these issues. I don't have a copy of it, but rest assured, you can find it at Amazon. Tell your friends, tell your neighbors. You don't have to read it, just have to buy it. Density. 3 parts to my density discussion. First, density is green. Then I'm going to discuss power density and then energy density. In my book, Power Hungry, these glasses under here are making all kinds of noise. There's about 15 of them, too. Okay. Density is green, power density, and energy density. In Power Hungry, I talk about what I call the 4 imperatives: power density, energy density, cost, and scale. I'll come back to power density, but let me just give you the punchline here. Density is green. We should be discussing and promoting density in everything. In fact, I'm working on another book, and that's one of the main topics I'm pointing to is density. We're looking at to make things smaller, faster, lighter, denser, cheaper. Density is green. Why is density green? Because it allows us to do more with less. But consider this, right? Who had the StarTAC or the original Motorola phone? It was like this big and about this wide and held 30 phone numbers. This is orders of magnitude more powerful. It's really a phenomenal computer, kind of a crappy telephone, but is a prime example of doing more with less. It is a prime example of the densification imperative. We want to do more with less. Small is beautiful. E.F. Schumacher's book in the 1970s, it was adamantly anti-nuclear, forget that. His phrase was exactly right, though. The green ideal is small footprints. Let me run you through some numbers on power density. I live in Austin. The city of Austin owns it owns 16%, of the South Texas Project, a 2,700 megawatt twin reactor facility in Bay City, Texas. The South Texas Project covers roughly 19 square miles, a land area about the size of the island of Manhattan. Do the simple math, and you come up with an aerial power density number. What is power density? Power density is a measure of energy flow. Remember, we're talking about energy is worthless unless or until we can make it flow. The faster we can make it flow, the better. The more joules per second, the better, the more powerful. 2,700 megawatts of capacity on 19 square miles, you get a power density number of 56 watts per square meter. That's the aerial power density number. Now let's assume we wanted 2,700 megawatts of wind generation capacity. As I explained just a minute ago, it won't be dispatchable capacity, but nevertheless, 2,700 megawatts of wind generation capacity. How much land area would you need? Roughly 1,300 square kilometers, or 25 Manhattan islands. Why? Because the power density of wind, and I can give you chapter and verse on this. I've looked at 17 different wind projects around the world. Power density of wind projects onshore is roughly 2 watts per square meter. 2 watts per square meter. What if we wanted to use biofuels? What if we wanted to use corn ethanol? The longest running robbery of American taxpayers in modern history. One of the most disgusting displays of pork barrel spending and favoritism in Congress. But I digress. What if we wanted to use corn ethanol to produce 2,700 megawatts of generation capacity? We would need a land area of 54,000 square kilometers, roughly the size of the state of West Virginia or 1,100 Manhattan islands. Why? Because the power density of biofuels, and I don't care if you're using corn ethanol, switchgrass, poplar, whatever, is measured in the fractions of a watt per square meter. I voted for President Obama. I won't do it again. Not lit up about Mitt Romney either. But the one energy policy that the Obama administration and Steve Chu have done that I think is truly disgusting and not based in anything, based in fact, is their continued push on biofuels. It makes no sense. The math doesn't work, and yet they're continuing to promote what I think is a disastrous policy. 40% of U.S. corn, 15% of global corn, 5% of all global grain is now being diverted into the U.S. corn ethanol scam in order to produce the energy equivalent of 0.7% of global oil needs. Power density. Power density. You all are familiar with the Macondo well in 2010 blew out in the Gulf of Mexico. It was a big mess. 50,000 barrels of oil roughly per day were coming out of the well bore. You recall we had live video footage from 5,000 feet below the surface of the ocean. Never mind that BP was out there doing what is the marine equivalent of the space program, and all of it privately funded. What was the power density had the Transocean Deepwater Horizon produced that 50,000 barrels per day? And there are many platforms in the Gulf of Mexico and elsewhere that are capable of producing that volume of liquids. The power density on the Deepwater Horizon would have been on the order of 127,000 watts per square meter. Why is BP out there in 5,000, 10,000 feet of water? ExxonMobil, Statoil, Hydro, Petrobras, Petronas, Shell, Chevron. Why are they out there in that depth of water taking company-killing risks? Because they are able to achieve on those offshore platforms power densities that would only other be achievable inside the core of a nuclear reactor. Throughout nature, throughout everything we do, power density is the way we are headed. The human brain has a gravimetric power density, that is watts per kilogram, 100,000 times that of the sun. It's a mind-blowing number. Happens to be true. Think about the sun. It's plasma. It's gaseous plasma. This is fatty liquid. 20 watts, 15 to 20 watts per kilogram of energy flow in the human brain. 1908, Henry Ford introduces the Model T. A 2.9-liter engine produces 22 horsepower. Today, you can buy a new Ford using their new EcoBoost engine, which was just recently named the International Engine of the Year. It's a 1-liter, 3-cylinder, turbocharged engine that produces 115 horsepower. In roughly a century, the engineers at Ford have increased the volumetric power density in their standard engine 15-fold and increased the efficiency of that engine 3-fold. Why? Because density is green, because density is where the money is to be made. I graduated from high school in 1978 in Tulsa, about 500 miles northeast of here. It was the beginning of the personal computer revolution. What were the personal computers what were the engines? The Intel 8086 processor. It had 29,000 transistors. Today, Intel's top-of-the-line processors have 2.3 billion transistors. In the roughly 35 years now since I graduated from high school, Intel has increased the computing power density of its best chips 78,000-fold and shrunk the size of the circuits by 99%. In everything we do, we are seeking density. We're seeking to do it smaller, faster, cheaper, better. And yet, what is the stated policy of the Green Left here in the United States and around the world? It's this. They want to replace high power density sources that are dispatchable, reliable, and low cost with low power density sources that are not dispatchable, highly variable, and high cost. Makes no sense whatsoever. Energy density. What is energy density? It's a measure of the energy that can be contained in a given volume or mass. So if we filled this with dry leaves, it'd have a lower energy density than if we filled it with gasoline, right? Why do we use gasoline? Why do we use diesel fuel? Because the energy densities are so high. Let me illustrate this by giving you a myth. The myth is that electric cars will free us from the evil clutches of ExxonMobil, BP, Hugo Chavez, the Saudis, the Venezuela, whoever you want to name. Here's the reality. Electric cars are the next big thing, and they always will be. The electric car has long been recognized as the ideal solution because it is cleaner and quieter and much more economical. It's a news clip from the New York Times, November 12th, 1911. Prices on electric cars will continue to drop until they're within reach of the average family. Washington Post, Halloween, 1915. The history of the electric car is a century of failure, tailgating failure. Why? Because the energy density of the best batteries is still lousy. Gasoline has 80 times the energy density of the best lithium-ion batteries. I was intrigued by Rob Gardner's slide on diesel fuel. Diesel fuel has even higher energy density than gasoline. Use diesel engines and hybrid technologies, you are really making some significant gains in efficiencies. Myth, we can quit using oil. The reality is that if oil didn't exist, we would have to invent it. Nothing else comes close to oil when it comes to ease of handling, flexibility, etc. Let me just run you through some what I think are interesting numbers, and I'm familiar with the ExxonMobil projections. It's interesting, just as a quick aside, to look at the differences between ExxonMobil and the other forecasters, BP, IEA, EIA, et cetera. They're all fairly uniform in terms of outlook for liquid fuels, at roughly 100 million barrels of demand by 2030, 2035, 2040 timeframe. But what's interesting to look at how ExxonMobil, and they are an unusual company. I mean, they don't go with the crowd, they don't trade, they have their own, it's their very distinct culture, and they've been a very profitable and very successful company. But if you look at their liquids projections, they're far different on a regional basis than other parts of the world. And I was fascinated by Rob's slide, particularly on Africa, where he looked at the working age population, which looked to be in Africa at about 1.2 billion people by 2040. That, I think, is why their numbers, projections for Africa and oil demand by 2040 show that demand there growing by 142%. None of the other forecasters have come up with that number. Where else does ExxonMobil differ in their forecasts? It's on coal and gas. Other forecasting agencies are predicting a huge future for coal, huge increases in demand. ExxonMobil is predicting that by 2040, coal demand will drop by 6% and to about 64 million barrels of oil equivalent per day. Meanwhile, they're extremely bullish on gas, far more than any other forecaster. They're expecting it up by 62% to about 92 million barrels of oil equivalent per day. That's up from about 57 million barrels of oil equivalent in 2010. Remarkable differences in how ExxonMobil is looking at the future of energy compared to their peers in terms of actually forecasting hard numbers. I wouldn't bet against them. That's my don't short Exxon, I guess would be my only investment recommendation. Top of the second inning. Let me just talk briefly about that in three points. Price, the industrial renaissance in the United States, and carbon dioxide. I mentioned carbon dioxide briefly earlier, so I'm going to give that a very brief mention now. The IEA in May said the U.S. had reduced its CO2 emissions more quickly than any other country on the planet. Why? Coal to natural gas switching. The abundance of natural gas combined with relatively expensive coal and the regulatory regime in the United States has led a lot of utilities to abandon coal and go to natural gas. Does that mean that coal will not be burned? Absolutely not. What happened in mid-August, shortly after the Indian blackout in early August, remember 600 million people in India lost power, an Indian coal company signed a 25-year, $9 billion contract to buy coal from a mining outfit in Kentucky. U.S. may not be burning that coal. The U.S. miners are going to ship it overseas. Price. October 25th, this is interesting to me. October 25th of 2008, this is just 4 years ago, the spot price for natural gas in the United States was $6.29. I didn't check it this morning, but we're at $3 and change. That price reduction of $3 per million BTU relative to just 4 years ago is resulting in a savings to the U.S. economy of $200 million a day, or roughly $73 billion per year. This is incredibly positive news. We can talk about employment in the United States. We can talk about the projections for increased oil production in the United States due to the shale revolution, the tight oil revolution. Bentech Energy is now predicting U.S. oil production will hit 12 million a day by 2022. That is a mind-bending number. In 10 years, the U.S. could be producing more oil than the Saudis or the Russians. Will that mean a big change in U.S. foreign policy? No. We're not going to let the Chinese control the Strait of Hormuz. We're not going to abandon the Israelis, the Saudis, or the Kuwaitis. But what that does for the U.S. in terms of industrial development, in terms of balance of trade, is phenomenal. The balance of trade, the issue of manufacturing, look at the manufacturing that is coming back to the United States. After years of chemical makers, fertilizer makers, et cetera, moving overseas, moving to Saudi Arabia, moving to Qatar, moving to Trinidad, they're coming back. PricewaterhouseCoopers just put out a report looking at petrochemical production in the United States. They're looking at estimates of $15 billion in new investment in petrochemicals here in the United States. Last year I mentioned, I met a guy named Dan D'Amico. He's the head of Nucor Steel. Nucor is the biggest steel producer in the United States. They're now building a $750 million direct reduced iron plant in St. James Parish, Louisiana. Why? Low-cost natural gas. They're substituting natural gas for metallurgical coal, reducing their carbon emissions, lowering the price, and bringing jobs and investment back to the United States. They may invest ultimately $3 billion and create 1,000 permanent jobs at their facility in Louisiana, all because of low-cost natural gas. When I asked him about this, and this is D'Amico talking, he said, we could change the entire manufacturing base in the U.S. if we just embrace what's happening in natural gas. It's a game changer for manufacturing, the trade deficit, and jobs. What is Nucor doing? They're investing in upstream assets. I know this on good authority. They have bought into drilling programs that assure them a flow of natural gas throughout the United States for the next 20 years. You could not imagine this just 4 years ago. 4 years ago, all the projections, including those from ExxonMobil, were that the U.S. was going to be a big importer of liquefied natural gas. And the question that was asked to Rob just a few minutes ago, what about natural gas exports? There are going to be natural gas exports from the United States. Will they be big? I don't know. Maybe one liquefaction terminal, maybe two. There will be export from Kitimat in British Columbia, is my estimate. But what does this cheap gas mean for the United States? A huge advantage over the Europeans. A huge advantage really over the rest of the world. The latest spot price for LNG in Japan is $17. This is a country that has to import everything. The spot price at Henry Hub now is $3 and change. What is LNG going to cost in Western Europe? What is pipeline gas going to cost in Western Europe? 2 to 3 to 4, maybe 5 times what we're paying here in the United States. What is the punchline here? We're going to create a lot of jobs in the United States. Are they green jobs? You know what? I really don't care. You call them purple stripe, paisley, polka dotted. They're jobs at a time when the U.S. desperately needs them. And to Obama's credit, he understands this, and he has talked about, in fact, the natural gas sector in positive terms, while also demonizing the oil and gas sector broadly, but nevertheless. Let me go on to my final point. End to end, natural gas to nuclear. I'm adamantly pro-nuclear, and I'm adamantly pro-nuclear, yes, in the wake of Fukushima. One person died at Fukushima. One of the workers at Fukushima drowned. He drowned. There have been no radiation deaths. There's been a lot of, I'm not minimizing the accident. It was a terrible accident. But in my view, right now, what is happening, we are moving toward nuclear inexorably. Why? Because it makes sense. Why? Because of power density. I'm adamantly pro-nuclear. In my view, if you're anti-carbon dioxide and anti-nuclear, you are pro-blackout. I'm anti-blackout. I'm adamantly opposed to blackouts. My energy policy is simple. I'm in favor of cold beer and air conditioning for everybody. We have beer drinkers here. I'm so glad. I'm a big wine drinker. Natural gas. Well, if it's not going to be nuclear, it has to be gas. What's happening now? Japan is importing as much natural gas as they can get their hands on. And yes, they're paying $17 for it. Incredibly high price. The Chinese are going to be paying the same kinds of prices. But nevertheless, why natural gas? Why nuclear? They're directly in line with 3 major megatrends that are underway globally: decarbonization, urbanization, and electrification. I love the slide that Rob Gardner showed. It's in the books about the share of biomass globally going down. What are we doing in terms of decarbonization? We're moving through the phases of matter, from solids to liquids to gas, the three phases of matter. We've gone from wood and coal, now we're firmly in the age of oil, and over time we're moving firmly and inexorably into the age of gas. And when we go into nuclear, we drop out solids and, we use uranium, but nevertheless, we go to nuclear, and the carbon drops out altogether. Decarbonization is the trend toward using fuels that contain less carbon. Wood contains 10 carbon atoms for every 1 hydrogen. Methane, CH4, 1 carbon for every 4 hydrogens. It's a 40-fold improvement in the carbon to hydrogen ratio. Decarbonization, urbanization. People all over the world are moving into cities. I recommend one book to you. It's Stuart Brand's book, Whole Earth Discipline. He wrote this. He says, every week there are 1.3 million new people in cities. That's 70 million a year, decade after decade. It is the largest movement of people in history. Another book, one written by a guy who's a fellow at the Manhattan Institute, as am I. He teaches at Harvard. His name was Edward Glaser. It's called Triumph of the City. He writes, the world isn't flat, it's paved. He goes on saying, cities are expanding enormously because urban density provides the clearest path from poverty to prosperity. What do people want when they get to the city? They want what we take for granted. They want lights. Electricity. The difference between the people in the developing world and the people that are rich is electricity. The countries that can produce cheap, abundant flows of electrons can bring their people out of the dark and into the light. It's that simple. I don't use PowerPoint. If I were going to show you one slide, it would be the table from Power Hungry, where I show you the top 20 countries ranked by GDP and the top 20 ranked by electricity generation. The correlation is almost 1 to 1. Africa is called the dark continent. Why? Because it's dark. 1 billion Africans use about the same amount of electricity as 33 million Canadians. Decarbonization, urbanization, electrification. The essentiality of electricity to modernity is incontrovertible, and that's why demand for electricity is growing so quickly. That's why countries like Vietnam are embracing coal as quickly as they can, because they understand to have a modern economy, to manufacture, they have to have electricity. I'll conclude by just saying a fairly obvious conclusion, I guess, when you think about where we've been and where we're going. The 19th century, from prehistory through the 19th century, we were in the era of solid fuels, coal and wood. 20th century has clearly been dominated by oil, and oil will continue to be dominant for a long time, particularly in transportation. But as we move forward in the 21st century, we will move more toward natural gas and nuclear, for all the reasons that I just mentioned: decarbonization, urbanization, electrification, densification. This is where the world is going. And it's essential that we produce more energy, and a whole lot of it, because we have 1.5 billion people who are still living in the dark. In 1865, one of the great economists in history, William Stanley Jevons, wrote a book called The Coal Question, in that book he wrote that energy is the universal aid, the factor in everything we do. With it, almost any feat is possible or easy. Without it, we are thrown back into the laborious poverty of early times. We need to produce a lot more energy so we can bring more people out of the dark and into the light. I appreciate your attention. Ed, thank you for the invitation. Questions, comments, I'm happy to hear them. Thank you. Comments, questions, disagreements? Yes, sir. Yes. I don't see, now, I understand why Rob Gardner said, well, we estimate, $30 to $60 a ton price. It could happen, I suppose, but I can't see it happening for a couple of decades. I mean, we've seen the last decade what's happened. Now, maybe we have more extreme weather. I don't know. Maybe it gets hotter. Maybe it gets colder. Maybe it's more extreme in both directions. But to me, that if it's more extreme, and it may well be, what does that mean for energy production? we're going to have a lot more energy in order to stay warm, cool, productive. So it's one reason why I'm so adamantly pro-nuclear, is that, and it's interesting to see how that is happening among the green left. There's an emergence. In fact, I've just been writing an article about the pro-nuclear Greens, and Stuart Brand is one of them. Mark Linus in the UK, George Monbiot, who writes for The Guardian, adamantly pro-nuclear, because as they look forward, they're saying, we have to have a zero or very low carbon source of energy that can scale. But if we're going to go nuclear, it's very expensive, and it implies a fairly high price on carbon. It's not free. Yes, sir.
At what price does natural gas get before we go back to coal?
What price does natural gas get before we go back to coal? That's a good question. And the answer is, I have no idea. I tried to predict price once, and I was so badly embarrassed by it, I thought, never again. But it's interesting, if you look at the Prairie State Energy Campus, this is the newest coal-fired power plant in the U.S. It's in southern Illinois, just about, it's 100 miles or so east of St. Louis. It's a state-of-the-art, it's not gasification, but it's a state-of-the-art coal plant, 1,600 megawatts, and they meet all the air quality requirements. It's a mine-mouth plant, but the total cost is something on the order of $4 billion. It's incredibly expensive. $4,000 a kilowatt, well, it's not quite that high, but nevertheless, that's far higher than natural gas is now. So all of the utilities are looking at this and saying, $3 gas, and we can assure ourselves of a price for the next 4 or 5 years if we, buy into the future market. The risk with nat gas is so low, that's what they're defaulting to. And, maybe some of this changes if Romney wins and the EPA backs off on the cross-state air pollution rule and some of these other things. But still, the coal sector and the coal-fired generation sector has to deal with coal ash. They have to deal with all the disposal issues for the mercury. They've got the mercury rule. I mean, they're under a regulatory barrage that even if Romney wins, I don't see necessarily abating completely. And therein is the challenge for nuclear. You didn't ask that, but Exelon has said, we can't build nuclear in the U.S. unless nat gas is at 8. Well, we have 4 reactors under construction, the Summer and the Vogtle plants in South Carolina and Georgia. They're only being built because those state utility commissions are allowing cost recovery in advance. No other states in the country are allowing that. But you talk to the guys who are building Vogtle, they're estimating 8 cents per kilowatt hour electricity for the next 40 to 50 years. And they're saying, look, we're willing to bet on that. We like that price. Sir.
Think about the latest discovery of natural gas in Mozambique, Israel, Cyprus, how they can influence to the price in the world uses.
Forgive me, your question is about nat gas in Israel?
In Israel, Cyprus, and Mozambique.
Yeah, this is fascinating, I think. It's you didn't mention Gaza. The Gaza gas field, 3 trillion cubic feet of gas offshore Gaza City. Hasn't been developed. It's the largest stranded gas field probably in the world that is easily accessible to huge markets in Egypt or in Israel. But the Israelis have prevented the Palestinians from developing it. But yeah, the Leviathan, the Tamar fields, what an incredible discovery. But it goes to Rob's point about the fact that we don't have a lot of gas globally. We have just a superabundance of natural gas globally. And the fact that it's emerging there in an area where populations are growing very rapidly, where electricity demand is extremely high. Look at Iran. There's a lot of talk about a nuclear Iran. We can't allow a nuclear Iran. It ignores the fact that the Iranians have one of the youngest populations in the Middle East and one of the highest electric demand growth rates in the Middle East. They need nuclear on a fundamental basis. Why? Because, again, a fact that is not known, widely told, the Iranians are net importers of natural gas. They're buying gas from the Turkmenis. So for the Israelis, it's great news because they can quit buying coal from abroad. They can fire their whole electric fleet with nat gas. They can bring that all ashore. But it also presents a lot of potential conflict areas between the Lebanese and the Israelis, between the Cypriots and the Greeks, which nothing new there, but and between the Israelis and the Egyptians. The Egyptians are already screaming about the gas contracts that they have with the Israelis, saying, well, we sold them at sub-market prices. We need to raise the price. So the gas politics in the Mediterranean, I think, are fascinating. And there's a whole lot of money going into there, but if done right, I think it's great, because the Lebanese are desperately energy short, in part because the Israelis bombed their power plants, but never mind. Yes, sir.
Coal will have any kind of impact in the near term, or is that, another 100 years because of the unconventionals?
Question is on gasification of coal. I don't think your question was whether it'll be another 100 years. Some of it's underway. The Duke Energy has the Edwardsport plant underway, but incredibly expensive. I mean, serious cost problems there. Gasification technology works. In fact, I'm going to Washington next week and talking at a gasification council or gasification conference. It works on municipal solid waste. It works in, interesting, one of the gasification technologies that I think is most fascinating is municipal solid waste on island economies in Puerto Rico, in Hawaii, and other areas where you have very high electricity prices generally because they're running diesel recip engines. You're talking 30 to 50 cents per kilowatt hour. Turning municipal solid waste into electricity makes some economic sense there. Coal is abundant. It can be gasified, but you have to compete with nat gas at $1,000 a kilowatt installed.
And how about liquefaction, the Fischer-Tropsch method with, a la Sasol
Right.
for personal transportation?
It's very expensive still. I've been to a CTL plant. I went to the Secunda plant in South Africa about 7 years ago. Until I went to Jubail in Saudi Arabia, it was the biggest industrial plant I'd ever seen. They had, I think, 8 of those huge hourglass-shaped, cooling towers at Secunda. And they just had a Chinese delegation there. So I asked this South African guy who was running us around, I said, well, so what did the Chinese say? And they said, well, their only question was, what do you do with the emissions? And you look around, and the emissions were easy to see for the whole way around the plant. It was this yellow-brown smoke all the way around the plant. So CTL has promise, and the Chinese are doing some of the Sasol technology, but again, it's very expensive. The more promising, you didn't ask this, but I think the more promising technology is gas to liquids. And there's a company called R3 Sciences out of Lafayette, Louisiana, that's working on a natural gas to methanol at the wellhead technology, which I think that, then you take the methanol, you could sell it for industrial use, or you have a pathway to gasoline. There's a lot of promise there. I think that appears to be all the questions. All right, I'll stop. Thank you very much.